Awesome. Yeah, thank you everybody for joining. I hope you're enjoying the conference. So today we're going to have a very interesting set of topics. So we're going to cover quite a broad range of the machine learning life cycle. And we're going to talk about some best practices that can be adopted and used at the different stages of this machine learning life cycle as you productionize your model, particularly around optimizations. So a bit about myself. My name is Alejandro Saucedo. I'm an engineering director at Seldon Technologies. So we do machine learning deployment and monitoring. We're the authors of one of the most popular machine learning deployment frameworks in Kubernetes called Seldon Core. I'm also chief scientist at the Institute for Ethical AI, where we develop frameworks that contribute to the responsible design, development, operation of machine learning systems in production. So we recently contributed to various European Commission policies on data and AI. Very interesting ecosystem, but I don't want to bore you guys to sleep, maybe for the beers. Shout out to Elena from Microsoft, with whom we did this collaboration. So this is a Seldon, Microsoft, and HuggingFace collaboration. So we've got some really great direction from the HuggingFace team. So we're very excited to not just showcase, but also get some feedback through the Jupyter notebooks that you guys can try out in the documentation itself. So what we're going to be doing today is we're going to be talking about the motivations of machine learning acceleration and also the challenges when it's not just for one model, but at scale. We're going to take a hands-on example. We're going to be using the hyped GPT-2 machine learning model. Perhaps the next talk is going to be using the DALL-E model, especially with the HuggingFace integration. We can now build some crazy-looking avocados. Then after that, we're going to be running the model locally so that we validate that our packaging works as expected, as the last thing that you want is putting it in production and then having to, as we were just discussing, call your DevOps team to send you the logs. That's one of the key steps that we're going to be delving, and then deploying the model through some kind of ways in which we can optimize the artifact itself, but also optimize the performance of inference of the model itself. Then we're going to touch upon very briefly. I know that this is a PyData conference, so specifically on the Python, on the data science, not a KubeCon. So we're not going to be talking too much about the Kubernetes, because again, I don't want you guys to fall asleep. But again, if you're interested, we can delve into that during the questions or afterwards. So yeah, talking a bit about the MLOps best practices and some things that you can put in place, and perhaps even as machine learning practitioners, point this to your machine learning engineer teams or DevOps teams so that they adopt it. In that way, you don't have to deal with Kubernetes, and everything is programmatic automation behind that. So let's start with the what. I guess just hands up of people that know of GPT-2. See if I have to explain it. Great, about 90%. All right, well, so just for the other 10%, GPT-2 model is a text generation model. It basically takes an input string as tokens, and it generates the next token. What this allows you to do is generate human-looking text, or human-sounding, human-reading text, that actually is used in some really interesting applications. The why is we have actually seen both really interesting and some controversial use cases of GPT-2. This one, Dungeon AI, if you may have come across it, is basically a Dungeons and Dragons-like text-based game where you choose your adventure. You say, hey, I've been dropped off into this magical world. What do you do next? And then you type, I will then go XYZ, and then it responds what you're looking to do. Of course, what they didn't expect was that the internet came in and started doing really dodgy and weird stuff with it. And regexes are not enough to just filter some of those crazy use cases. But today we're not going to be delving into the nuances. I do have an AI ethics talk that I actually gave at the PyData last year, so also recommend you to check that one out if you're interested on that general topic. And then the how. So this is the thing that we actually talk about, but just in a more intuitive way. We're going to use the HuggingFace hub to pull the pre-trained models. So we're not going to be sitting here for a couple of hours until our models train. We're going to be using those pre-trained artifacts. Then we're going to perform some optimizations using the HuggingFace Optimum library. We're going to talk about what that means, as well as what the formats available are, in this case the ONNX format. And then we're going to be, as I mentioned, running it locally with our server called MLServer. Once we're ready, we're going to deploy this into Kubernetes using Seldon core and then productionizing our stack. But we're going to be focusing mainly on the points on the top. As a reminder, so the code examples and links, you'll find them in the slides, and all of that was in this bit.ly link at the top, which will be at the end of the slides as well. So if you want to try anything that we're showing, you can. It's in the documentation if you can find it. So please check it out. Something breaks, open a GitHub issue. That's the beauty of open source. So let's start with the first step. So fetching the model with the HuggingFace hub. So this is actually quite simple. The only thing that we need to leverage, given that we're using a pre-trained model, is we can first fetch the model itself, and we're going to explain what that actually means from an intuitive perspective. So you can do the tokenizer from pre-trained, that actually loads the tokenizer, and then loading the model from pre-trained again. This actually goes into the hub and finds the repo with this specific name. You can then build a pipeline, which simplifies a lot of the steps for inference. But just to give you a little bit more of an intuition of what's actually happening under the hood, let's say that we have this input text, this string, I love artificial intelligence. What we need to do in order to run this through the model to generate the next token, we actually have to convert it into tokens, right? So basically, machine-readable data inputs that we can pass to our model. We can use the tokenizer for that. That means that we run tokenizer.encode. We actually get those tokens. We can now generate that next token. However, you can see that here we're generating multiple tokens. So this generate function has some magic inside. We're going to see what that is. But what this is doing is actually generating multiple new tokens. So basically taking the text, generating one token, then taking all the text plus that token, generating the next one, etc., etc. And then by the end, we have to just decode it using our tokenizer itself. So now we have this generated text. I love artificial intelligence, but I'm not sure it's worth. So that's very simple. Now, the only thing to mention is that this generate function has some magic inside. The way that you generate the tokens can be basically in a naive way, where the actual prediction, the actual response of the model itself gives you all of the tokens with the logits that it predicts as the probability of that next token being that generated one. You can actually take a greedy approach and just take the most, the one with the highest probability at each step. However, you can use other algorithms like beam search, which in this case the generate function does, which actually has a look ahead, right? It tries to generate best by looking at multiple steps beyond, as opposed to just a greedy approach. So, the pipeline method that we used here, this actually does all of that for us, right? So whenever we run the prediction with our pipeline, it does kind of like that magic for us. And I'm just providing you some of the intuition, as this is something that we're going to be reverting back. More importantly, those parameters are what we're going to be defining as our machine learning as code when we are deploying our models. So now we go to the next step, right? Of course, right now we could actually just deploy that model. If we wanted, we could even modify that model itself. We could do some transfer learning and then push the new updated model into the hub and then work with that. In this case, we're going to be optimizing that. And by that, we mean quantizing the model and converting it into an output format that can be optimized, in this case, the ONNX format. So ONNX is a standard that has been worked now cross-functionally. It's part of the Linux Foundation, was donated by Microsoft, and it provides a standardized format to represent models, but also a standardized format to be able to optimize the runtime of those models itself with servers like Triton or the ONNX runtime, etc., etc. If you have actually used Triton with ONNX, you may have faced some of the pains of having to create those config files, so it's a little bit non-intuitive, at least initially. Fortunately, we can leverage one of the newest libraries from HuggingFace, the one that we actually perform our integration with, which is the Optimum framework. So the Optimum library provides an interface to convert, quantize, optimize our models, export them into ONNX with very similar interfaces to what we saw. So instead of just using our tokenizer and model functions, we would use the Optimum specific functions that would allow us to actually run and load those optimized models itself, and it would have kind of like that ONNX runtime in the background. So this is basically just telling you as data scientists, you can just stay within Python and interact with a very simple kind of interface while still getting the advantages of that sort of underlying runtime that can be optimized against specialized hardware like GPUs or TPUs. So okay, so now we have the artifacts. We now have an optimized artifact. Now is the next step of actually testing it, running it locally before we deploy it. For that, we're going to be using this library called MLServer. So before talking about the actual steps, we do need to talk a little bit about the complexities of going into I have a model that is ready to generate value and be deployed, and I already have it generating value and it's running consistently. There are challenges on not just specialized hardware. We talked about the requirements of things like GPUs or TPUs, but especially with transformer-based models, you will have some of them that require a lot of memory, right? And when it comes to that, you have scheduling considerations. Yeah, even if you want to perform optimizations that involve horizontal scaling or vertical scaling, that has requirements on the hardware where you run it with and how you optimize that, right? If you have a bunch of like scikit-learn models that are much, I guess, smaller, you may want to actually leverage some hardware for those versus the more heavy ones on the others. So that's one consideration. There are complex dependency graphs. There has been a lot of talks around data-centric machine learning. So this is actually quite important, especially when it comes to transformer-based models. You actually have a preprocessor model and post-processor steps. But even with other models like with DALI, we actually see that there are multiple steps in the pipeline to generate whether it's filtering, prioritization, et cetera, and you have use cases in machine learning like recommenders, systems, or search that does require a lot of different steps. So there are complex dependency graphs across the data flow. There are compliance considerations, right? If something goes wrong, if you need to explain a prediction, you need to have the infrastructure to be able to go back, to rerun things, to ensure that everything is, like the last point, reproducible. And making sure that that reproducibility goes not just on the sort of atomic components of the model that you're deploying, but across the overarching infrastructure, right? Remembering this data-centric approach that you need to consider all of the different parts at play, including the data with the artifact that it runs at that time. So what we're going to be actually skimming through, but covering, is how we're going to be performing those steps. First, the conversion of that artifact into a fully fledged deployed service. We're going to be first talking about the MLServer component, right? That's the ability for a data or machine learning engineer to be able to test it locally, but more importantly, even build a reproducible pipeline that then allows for this to be automatic. And then we're going to be talking about how that would allow you to go to the next step, which is actually the productionization. So running it locally with MLServer, is quite simple. You need to first just define that pipeline programmatically. You then are able to run it locally with some of the command line interfaces that you have, and then you can deploy it as the follow-up steps. So I was requiring kind of like to pay attention on the Python classes, because there is really a one-to-one mapping between those Python classes and the configuration that is available for you to actually modify. So whenever you use the MLServer HuggingFace runtime, there's other runtimes like LightGBM or scikit-learn or XGBoost, etc. But specifically the HuggingFace one exposes these parameters, right? First of all, you have the ability to specify which task you want to leverage. That's the pipeline itself. In this case, you saw we were using text generation, but we're going to also show how you can do question answering, or you can do sentiment analysis, as well as the many other tasks that you have at hand. You can then specify the pre-trained model. This is the repo location of the HuggingFace hub where you're going to be fetching it on. And then you have the ability to actually toggle whether you want to use the optimized models or not, right? So it very much is like your model as code configuration based, so that it's reproducible whenever you want to rerun it. Of course, this has a caveat. That is something that we normally emphasize, and maybe this is diverging a bit, but that requires, to a certain extent, idempotency on the buckets, right? On your HuggingFace hub, right? By name. So this means that if you want to rerun this thing and it pulls the artifact, you're not just overriding it without versioning it in the artifact itself, because otherwise you don't have the idempotency on the definition by the configuration itself. The second step is to actually just run it, right? After you create that config file, the only thing that you need to do is run MLServer start. that actually runs with fast API underneath. It actually has like some architecture where the fast API is the service orchestrator, and then you can have like multi-processing of your models within the Python itself. And then that means that you can actually consume that component, right, the model that we deployed. So you can send an input of Seldon is very, and then the prediction is the generated text. Seldon is very curious about the matter, blah, blah, blah. Right? So pretty cool initial overview. So let's have a look at an initial overview of the demo itself. So, we actually have a repo. This was from the KubeCon showcase. You can actually open it directly with the code spaces. So this is actually something that I had not known about, but it's pretty cool. It gives you like a fully fledged environment. Here you can see that we've already defined that config file. It is the text generation configuration using the distill GPT-2. This is the actual smaller, slightly smaller model, because otherwise, we would be waiting here for it to download the multiple gigabytes. Then we actually run the MLServer start. What MLServer does, it actually runs that HuggingFace step. It pulls the model, so it downloads the whole internet, those 2 gigabytes. And you can open the Open API documentation, where you can actually consume it interactively. This is again important, right? Because you want to make sure that you test it. In the case of the HuggingFace models, maybe there's a little bit more of a simpler deterministic behavior. But when you have like a custom Python artifact that you're releasing and deploying, there may be some challenges. So here you can see that there has been an automatically generated one that says I love artificial intelligence, and it generated if you're an AI, you would love to know something. Right. So so you see that it's quite simple. You can now modify the task itself. In this case, the text classification is a sentiment analysis. You see that we remove the pre-trained model. That means that it just downloads the default one, which is a BERT model. You can see that it actually downloaded the distill BERT, which is the smaller one. And now, if you actually send the request in there, which is also the I love artificial intelligence, then you can see that, there is a response of a sentiment analysis positive with 90-something% probability. Right, so that's basically it. It's very sort of like simple, and that should show you kind of like the steps that you can carry out. And if you go into the documentation, you'll have like all of the tasks that you can basically run through for sentiment analysis, etc. So now we're going to actually start diving into some of the more interesting parts, which is, of course, the deployment one, but how we can leverage some optimization steps so that we can showcase how with GPU we can run parallelization of multiple inputs with things like micro batching or adaptive batching or micro batching, and we're going to talk a bit more about what that is. So now that we see that it runs locally, we can move to the next step and just productionize our model, right? Put it into our scalable infrastructure that is going to have that specialized hardware and is going to perform the right and relevant scheduling across the different areas. So for that, we're going to be using Seldon Core. So this is basically the Kubernetes-based deployment framework. Not to bore you to death, the main thing that I want to emphasize is that those parameters that we had within MLServer have a one-to-one mapping with what you would define in the custom resource definition. So, at the infrastructure level, you would still be able to have that item potency with all of the models that you have deployed based on the configuration specifications of that. So yes, it's one-to-one aligned with those. And again, the way that you would deploy it is very similar, but instead of running it in MLServer, you would actually run that against the cluster. It would, pull the artifact. It would run that REST, gRPC, and Kafka interface, and then you can actually consume that model through the same method, right? The same API. And the only other thing to emphasize is, when it comes to the way in which we actually serve the models, the protocol that we use is a protocol that we've worked cross-functionally across multiple different players in the industry with the Triton team, the Kserve team, now the MLflow and TorchServe teams. They now all have standardized to this protocol, which is great, right? Is looking towards making sure that we not all have like different schemas, different payloads across different areas, and we want to continue driving forward kind of this adoption for this protocol. And similarly, right now we're using the HuggingFace framework, but you can run Triton underneath and deploy those models. But yeah, that's kind of a bit of divergence. So now the final step is how do you make sure, as us as practitioners, as data science practitioners, that you don't have to deal with these final steps of actually deploying into Kubernetes. This is quite important to make sure that there is some programmatic automations so that data scientists can focus on doing data science, and whenever models are ready and tested locally, they are actually productionized in a way that it's seamless for them to not have to become experts in Kubernetes or even knowledgeable to an unreasonable extent into Kubernetes to be able to see whether their actual models are being consumed. Some of the best practices that we're going to be covering is things like GitOps. So this is basically being able to deploy into the production environments, not by just modifying the environments, but instead by actually having a config as deployment, right? So you put your configuration and that syncs consistently into your production environment. That means that whatever you have in your, in this case, version control system, GitHub repo, is exactly what you have in your production environment. And that's good for many reasons, not just for the sake that you can have reproducibility, right? The fact that you can actually go to the model that was deployed last year, but also if there are some disaster recovery mechanisms. If your cluster goes down or needs to be migrated, you can actually do so by just copying kind of like the state into a new environment. So we're going to be actually doing that. Again, as we mentioned, the data scientists should only focus, or not should only focus, but their main sort of focus is on the data science side and potentially some of the machine learning engineering, but to create kind of like this models, to build what is artifacts at the end that can be productionized. Then the machine learning engineer itself would be able to create those programmatic pipelines that map into the specific use cases, introducing things that are well beyond the scope, but covering things like validation, integration tests, unit tests, and also making sure that you can create all of those service level indicators, service level objectives that you're expecting to meet in production. Right, and this could be things basic like accuracy, precision, recall, with the operational processes that involve the assessment of those steps, but more importantly, making sure that it is specific to the use case, right? So the machine learning engineer will be able to create those pipelines, and then you would have that programmatic flow that whenever a model is ready, it can be productionized or it can be marked as ready so that they can be assigned off to be deployed. The way that we're going to be showing this is actually integrated into Azure. Using this GitOps tool called Flux. Flux basically just maps into a Git repo, and it just syncs that Git repo into a Kubernetes environment. So let's actually dive into the final demo. So here you can actually see that we have a configuration of our Kubernetes cluster. This Kubernetes cluster itself is going to have some GPU nodes, because we're going to be running some benchmarks. To show how this optimization benefits on different areas, and we're going to be actually showing how we've configured already this GitOps integration. So we have this Git repo containing the deployment specifications. This is what is going to be synced every time that we modify this specific deployment manifests. That is what is going to be synced in the cluster. This actually has a CPU and a GPU deployment. Using that HuggingFace server and those parameters that we talked about. So that has the text generation model using the distill GPT-2. The only difference is that you can see the device itself. We have a device that is device 0 or device 1. That is whether it's the GPU or not, as well as to make sure that it's running in the GPU nodes themselves. Right. So that's the key thing that we need to just see. Once we actually configure this integration, that means that we're going to see the models being deployed. And once the models are deployed, then we can actually start consuming them. So here we can actually see that the synchronization started. The models are now running in the Kubernetes cluster. And similar to what we did in the past, now we can actually just consume them by sending requests, right? So we now have like a CPU model that is deployed and a GPU model. Both of them are GPT-2 inference servers themselves. So we can actually reach through them via the endpoints themselves. And those are kind of like the parameters that we've covered. So now the way that we're going to be running some of these tests is using this tool called K6. So this is a very cool benchmarking tool, which will allow us to actually just run a benchmarking job to test what is the request per second and capabilities for the GPU versus the CPU one. Here you can see that the GPU heavily outperforms the CPU model itself, and this is of course in a way expected. Primarily when it comes to the way that we're testing it, it's actually by sending batched micro-batched inputs, right? And just kind of like to emphasize on that point, this micro-batch inputs is what the model itself needs to perform faster than the CPU one. Otherwise, it would perform about the same speed, right? If they are processing it one by one, it's going to be almost the same. In this case, it actually like performs it in a single GPU clock speed, right? So you can have like 100 or 300 at once, and you can see like 10x, 100x improvements between those. So that's the first iteration of the showcase. Now what we're going to be doing is showing another sort of technique that we can introduce for optimization. This is not micro-batching, this is adaptive batching. So whilst micro-batching, we're actually performing the batching itself in the client, right? We're actually like packaging 100 requests, sending 100 requests, and receiving 100 responses. What we're going to be doing is we're going to be doing adaptive batching, which means that we're going to be sending one request at a time, and then in the server itself, we're going to say for a window of time of either 2 seconds or 100 requests, we are going to actually batch them into one, and we're going to like run them in inference at the same time, right? So that's what we're going to be able to see, and that will also show us how we perform and maximize the utilization of our GPU and also our CPU in this context, right? Because this is something that we were discussing, is something that you want to make sure that you're using. If you're spending a lot of money in specialized hardware, you want to make sure that you're actually utilizing it at its maximum, right? So that's one of the key things that you want to make sure that you do when performing those things. So let's actually like dive into some of those parameters. So here you can actually see in the parameters that the only thing that we have to specify, and you can also test it locally, is the maximum batch size. So that's basically how large the batch is expected, as well as then the maximum batch time that you want to run it against, right? So it's either or. It either reaches, in this case, 128 requests, and then like passes them to the GPU, and then like sends them back to all of the relevant open connections. Or if like 3 seconds pass, then it actually like takes whatever it has and then runs that against the inference itself. So, and the interesting thing about this is that it is important for you to actually run the relevant benchmarks to tweak what is the best optimization for both your model and the hardware itself, right? So here you can see that we're running another benchmark test. We're going to be seeing an even better improvement, and you can see here that actually the requests are being batched in terms of the inference itself, right? So every couple of requests, it actually performs inference once, whereas here it actually would perform inference every single time as the requests go through. So that's basically the overview of some of the optimizations that you can do once you actually deploy your model. And one of the things that we skimmed through, but if you're interested, some of the resources here delve into the monitoring considerations, right? All of the principles, best practices around machine learning monitoring, not just for operational monitoring, which is basically requests per second, latency, but also for advanced machine learning monitoring, which goes back into the data-centric machine learning because it includes drift detectors, outlier detectors, adversarial detectors, and those themselves are models which also require specialized hardware, which also at risk. So you do open into considerations even when you introduce things that in theory reduce the risk within your machine learning stack. So that was kind of like the initial overview. What we actually were able to see was very, very broad. We were able to see how individuals are able to convert, in this case, data into machine learning artifacts, whether through a Jupyter notebook manually or using some ETL workflow-based system. Then being able to deploy these artifacts either manually or through some programmatic CI/CD methodology, as well as through GitOps itself, and then the ability to productionize those artifacts once they have been tested and validated locally. Some things that we didn't discuss was the advanced monitoring techniques, which you can delve into, but will still reflect into some of the optimization considerations that we discussed. You may also want to introduce optimizations to your drift detectors or outlier detectors, et cetera, et cetera. And then, of course, the loop back of the inference data that goes through, to make sure that you can take advantage of that in your training data. As I emphasized, all of the resources, you can find them in this link. So, we have tons of other talks, actually several that were at the PyData in the last couple of years. One that dives into CI/CD for production machine learning, on production machine learning monitoring with drift detectors, outlier detectors, explainers. This one on accelerating ML inference at scale, and then a more recent one, which is now actually a very important topic of machine learning security and the concept of best practices. Actually, we talk about it as bad practices through flawed machine learning. So first identifying what we shouldn't do, and then defining what we should. Just to summarize, today we were able to actually delve into some of the motivations of machine learning acceleration. We talked about our recent collaboration with Microsoft and HuggingFace to bring this integration with the HuggingFace hub, as well as these optimizations that can be done at the artifact and also at the inference layer, and then some best practices that can be introduced to minimize the interaction with MLOps where possible. So with that, thank you very much, and I'm more than happy to answer any questions. So thank you all.
Lovely. Thank you, Alejandro. Questions for Alejandro? One at the back. There we go.
Thanks for the talk. Really interesting. Wanted to ask, how does Seldon compare to SageMaker Inference or even HuggingFace Inference API?
Yeah, that's a great question. So HuggingFace, recently they have the integration with Azure, so they allow you to deploy endpoints. So that basically is, in a way, a managed service that allows you to just integrate with that. SageMaker does also provide serving of their containers. Again, very well integrated with the SageMaker ecosystem. Seldon Core itself is more like a set of, MLOps Lego blocks that allow you to bring it into your own infrastructure. So this is Kubernetes cloud native. And the way that we built it is so that it integrates with all of the broad set of heterogeneous model training systems, MLflow, also SageMaker, Vertex AI, Azure ML, et cetera, et cetera. So it really is more for use cases where you're building your own internal MLOps platform. So I think that's the primary use case that we see. However, having said that, you can see that there's a lot of intersection and collaboration with some of those other platforms, primarily because there's also relevant use cases for those which are potentially more vertical. Seldon tends to be seen more as kind of like that central serving platform, like the DevOps environment, where all the sort of models kind of like get orchestrated into. But yeah, probably more resources are in the documentation, so I definitely point you to that for you to check kind of like the full list of features. Mm-hmm.
Love yourselves. Any more questions for Alejandro? There we are. One over here.
Thanks for the talk. It seems that the kind of a framework that you presented is in a sort of sweet spot between data science and DevOps. So, like in more traditional teams, they have like data scientists and have DevOps. So, who is actually responsible for building and maintaining that? So, like, how do you reduce the tension between data scientists and DevOps?
That's a great question. Yeah. So that is a really good question. So the way that we see it, and this is of course still kind of like an incomplete work in progress picture, as we are all figuring it out. The way that we have seen it is that there is starting to become kind of a standardized organizational structure where you would have data scientists, machine learning engineers, and DevOps engineers, each of them with kind of like a smaller ratio, right? Like you would have perhaps one DevOps engineer to multiple machine learning engineers who are maintaining multiple use cases, which are kind of like being continuously provisioned by multiple data scientists, right? So what we see specifically on who builds the infrastructure, we see it as multiple different levels. We actually agree that, I totally agree with your point that this does seem to be quite an interesting sweet spot because this machine learning engineering has been the intersection where we have been able to see where we can kind of like touch some of the use cases and user base of HuggingFace, which is primarily more kind of like on the data science and machine learning engineer. Seldon Core is more on the DevOps and machine learning engineers. So we tend to see that machine learning engineering function itself is the one responsible for building what I refer to as use case pipelines, right? So these reproducible programmatic integrations with ETL or CI type pipelines that allow for that continuous delivery of a particular machine learning model type use case. So I would say that role is the one that tends to kind of like help reduce some of the friction. Having said that, there is still some ambiguity where you find a lot of data scientists working into the machine learning engineering roles, building their own sort of like fast API or Flask wrappers, and then deploying them and then realizing, oh no, now I am actually having to like be careful with the uptime, be responsible of the uptime of my service. And they're like, okay, DevOps person, your problem. So I would say, yeah, the machine learning engineering function is kind of like the one responsible building kind of like those integrations, but not the infrastructure. That would still be kind of like DevOps. Yeah, so hopefully that gave a little bit, more picture.
Lovely stuff. So that's your call time there. Alejandro will be around afterwards to answer questions if you have them for him and haven't been asked them at the moment. But before that, another round of applause for our speaker.